Welcome to the video. In this one we will be talking about how to solve systems of nonlinear equations so that by the end of this video you will be able to use Newton's method to solve any system of nonlinear equations. So let's start a little bit simpler and begin just with two nonlinear equations instead of just jumping in with n nonlinear equations. So let's do two. And those two nonlinear equations have to be solved together. So we have one equation f1 that is dependent on, let's say, two independent variables x and y. We want to set that equal to 0. And we want to have a second nonlinear equation f2 that is dependent on x and y equal to 0 at the same time. And in order to solve this system of equations, let's use Newton's method again. So we start by choosing a solution estimate x0, y0, close to the true solution. And the true solution is made up out of two components, x true solution and y ts, y the true solution value. So then we write the Taylor series for x ts and y ts, starting at our initial guess x0 and y0. So that means that f1 of the true solution values x and y would be equal to, well, it's equal to 0 if x and y are our true solution. And that then, using the Taylor series, would be f1 evaluated at our initial guess x0, y0, plus the distance x true solution minus x0 times the partial derivative of the first function with respect to x, evaluated at our initial guess x0, y0, plus the distance y true solution minus y0 times the partial derivative of f1 with respect to the second independent variable y, evaluated at our initial guess x0, y0. And then we have infinitely many terms in order to make that an equality. Let's do the same thing for f2, our second nonlinear function. So the second nonlinear function evaluated at the true solution values of x and y is again, of course, equal to 0. But if we do a Taylor series expansion around our initial guess x0, y0, we get that f2 evaluated at our initial guess xy0 plus, again, x true solution minus x0 times the partial derivative of the second nonlinear function with respect to x plus y true solution minus our initial guess y0 times the partial derivative of the second nonlinear function with respect to y, evaluated at x0 and y0, and then plus infinitely many terms. Now, if we truncate this Taylor series as we did before, then we won't get the true solution anymore, but we will only get an improved estimate for the solution. Let's call it x1, y1, and recall that if we write in the superscript in round parentheses a number that indicates the iteration number that we have, starting out with the initial guess, an iteration number of 0, and then updating the solution once will get us to the iteration number 1. So let's use the Taylor series expansion, replacing the true solution with our updated estimate x1 and y1. So we get 0 is equal to f1 evaluated at our initial guess x0, y0, plus, now here the true solution cannot be achieved, so we will just replace this with our updated solution estimate x1 minus the x0, the rest remains the same, times the partial derivative of f1 with respect to x, plus in this term here, y can't be the true solution anymore, so that will just be our updated estimate y1 minus the rest of this equation that we then just copy over. And we've truncated away now these infinitely many other terms. Let's jump to the second equation. We start out again with 0 is equal to f2 evaluated at our initial guess xy0, plus, in this equation again, the true solution is replaced by our updated estimate x1, minus the rest that we just copy over, and then the y here in the true solution, the y true solution in the second equation is replaced by y1, and the rest of the equation is just copied over. All right, so we have here two equations. And before we try to solve this, because this looks like a rather lengthy equation, let's introduce a couple of shorthands to make this equation a little bit more compact. And the shorthands are simply that I'm going to call the difference between the updated solution x1 minus the original estimate x0, I'm going to call that delta x. And similarly for the y variable, I'm going to call delta y the difference between the updated estimate y1 minus the original estimate y0. So let me substitute this in. So I get f1 evaluated at my initial guess xy0 plus, this is the difference in the x value, so that's just delta x times the partial derivative df1 dx evaluated at xy0 plus here you'll see that this is delta y, so plus delta y times df1 dy evaluated at the initial guess xy0. And that's equal to 0. For the second equation, we have f2 evaluated at the initial guess plus, this again here is delta x times df2 dx evaluated at the initial guess plus this difference again is the shorthanded by delta y times df2 dy evaluated at the initial guess x0 y0, and that is again equal to 0. All right, so if you look at these two equations, you'll realize that this is a system of two linear equations for the unknowns delta x and delta y. Right? We know the functions f1 and f2, and we know an initial guess x0 and y0, and in a Newton's method, we should be able to calculate the analytical partial derivatives of the functions f1 and f2. So the only thing that we don't yet know in these equations is the delta x and delta y. That's our unknowns that we then want to solve these equations for. In order to do this, because it's a system of linear equations, let's write this in matrix form. So our vector of unknowns is delta x, delta y. And the first equation here multiplies the delta x by df1 dx. And the delta y is multiplied by df1 dy. So that goes into the first row of the matrix. And the right-hand side of this equation, right, if I move that f1 over to the right-hand side, the right-hand side is minus f1 evaluated at the initial guess x0, y0. Let's do the same thing for the second equation. So what multiplies delta x and delta y? That goes into the second row of the matrix. So the delta x is multiplied by df2 dx, and the delta y is multiplied by df2 dy. All of that, the entire matrix here, evaluated at the initial guess x0, y0. And on the right-hand side, we have the f2 that we move over. So we have minus f2 evaluated at x0, y0. So this are these two linear equations just written in matrix form. Okay, so let's take these and let's solve this matrix system. And it's a 2x2 system, so it's straightforward to use, for example, Cramer's rule. We don't really have to go use the Gauss-Jordan method. We could, of course, but let's just solve this analytically with Cramer's rule. Okay, so if we apply Cramer's rule, then delta x would be equal to f2 times the partial derivative of f1 with respect to y minus f1 times df2 dy divided by a j that I'm going to talk about in a second, and we get the delta y accordingly using Cramer's rule. Now the denominator in here, right, if you remember Cramer's rule, it divides by the determinant of the matrix. So that's what we shorthand here by J, because that's called the Jacobian determinant or the Jacobian matrix determinant, or for short, just the Jacobian. And that Jacobian is the determinant of that partial derivative matrix df1 dx, df1 dy, and then df2 dx, df2 dy. The determinant of that. Okay, so this is the solution for delta x and delta y. And then we can use this change in the estimate of the solution to update our solution estimate. Right? Just using the definition of delta x, we then get that our new solution estimate x1 is the old one, x0 plus the calculated delta x, and the new y at iteration number 1 would be the old initial one, y0 plus our calculated delta y. And then we would repeat this process, replacing x0 and y0 with x1 and y1, until we are satisfied with the accuracy of our solution. Now, how do we determine this if we have a system of nonlinear equations, so multiple solutions, x and y in this example? Well, in that case, we have to look at the norm of either the tolerance in function vector or the norm of the estimated relative error vector, and check whether that is below an acceptable value. Now, which norm we will use, the infinity norm, 1 norm, or 2 norm, or Euclidean norm, depends again on the application. For example, if you're interested in the largest error in any one of the solution variables, you would use the infinity norm. Okay, let's do an example for two nonlinear equations. Here's an equation f1. X squared plus y squared minus 1 is equal to 0. And a second equation, x minus 2 squared plus y minus 2 squared minus 4 is equal to 0. And the task is find the x and y that solve both equations simultaneously. So let's first look at these equations a little bit and see whether we can't get a feel of what the solution should be by graphically looking at these equations. So let's look at the first equation. If you look at this, x squared plus y squared minus 1 equal to 0, you might realize that that is the equation of a circle with the origin, with the center being at the origin of the coordinate system and the radius of this circle being 1. So this equation just graphs out as a circle. So all solutions to this first equation, there are infinitely many, but they all lie on a circle of radius 1 centered on the origin. And knowing that the first one is a circle, if you look at the second equation, you'll quickly hopefully realize that this is a circle as well, except the center is not at the origin. The center is at x equal to 2 and y equal to 2, and the radius is equal to 2. So let me draw this. And just graphically, you can see that these two circles, right, the second circle being all the solutions that solve the second equation, that when we're after those points that solve both equations at the same time, we're looking at the intersection of these two circles. And in this case, there's one intersection and there's a second intersection graphically over here. So this system has two solutions. Okay, so now let's not try to solve this graphically, but let's try to solve this using Newton's method. So Newton's method starts out with, here are the update equations for delta x and delta y. And you'll realize that there's a whole lot of partial derivatives in here. In fact, here the Jacobian contains all the partial derivatives that you can have, right? The first function with partial derivatives with respect to x and y, and the same thing in the second row for the second function. And with any Newton's methods, what we will have to be able to do is calculate those partial derivatives analytically. So that's how we will start out with, as the first step, calculate the partial derivatives analytically. Okay, so let's go. We have our function f1, we have our function f2, and all we need to do is calculate df1 dx. So my f1 function is this guy here. So I'm taking the partial derivative of this with respect to x, and that is equal to 2x. Then I need to calculate the partial derivative of the first function, the same function, with respect to the second independent variable, so with respect to y. So partial derivative of that is 2y. And then I can move on to the second equation, this one here, right? And I have to calculate the partial derivative of df2 with respect to x. So that would be 2 times x minus 2, inner derivative is 1. And then I have to calculate the partial derivative of f2 with respect to y. And that's equal to 2 times y minus 2. Okay, so those are the partial derivatives. And then I can go ahead and calculate what this Jacobian is, right? Because I've calculated now all of these partial derivatives. So now the Jacobian of these two functions, f1 and f2, is the determinant of df1 dx, which is 2x, df1 dy, which is 2y, and then df2 dx, which is 2 times x minus 2, and then df2 dy, which is 2 times y minus 2. And I want to calculate the determinant of this. So this times this minus this times this. So we get 2x times 2y minus 2 minus 2y times 2x minus 2. Okay, let's simplify this a little bit and multiply this out. So I get from the first term 4xy minus 8x. And the second term here has minus 4xy plus 8y. Okay, and then you'll see here that the 4x minus the 4xy cancels, and I get 8 times y minus x. That would be the Jacobian. Okay, and now all that's left to do is evaluate the delta x and delta y, because I now know all of these functions, and then update an initial guess. So the thing that I haven't talked about yet is what is the initial guess for this problem. And it's not given in the example either. So how can you get an initial guess? Sometimes it's helpful, like we did before, to graph the individual nonlinear functions. So we saw that there are two solutions here. And let me just make up an initial guess. So I'm going to come up with an initial guess. And sometimes it's helpful at least to start out with these type of methods to, when you do them by hand, to come up with an initial guess that is easy to evaluate. So let me choose as an initial guess x naught is equal to 0 and y naught is equal to 1. Now, interestingly enough, I can choose y naught equal to 0 because that would make the Jacobian here 0, right? And if the Jacobian is 0, then I can't invert this linear system. It doesn't have a unique solution. So that's one of the failure modes, right, or that we can already see of this method if the Jacobian turns out to be 0. So that's why I choose here y naught equal to 1. Okay, so that's an initial guess. And just for practice, let me calculate the infinity norm of the tolerance in function, just to get a feel of how well does this initial guess actually solve these two equations. So let's calculate the infinity norm of the tolerance in function. Okay, so we have two functions, right? So therefore, the tolerance in function will be a vector. So what will that vector be? It will be the absolute value of, well, F1, where I plug in my current initial guess. Okay, that's the first entry. And the second entry is the second function, where I plug in the same initial guess. Okay. That is the, that's right, I want to calculate the infinity norm of this. Okay. So let's do this. So F1, if I plug in 0, 1, so 0 and 1, that's 0, plus 1 squared is 1, minus 1, that's 0. Okay, so the first entry here is 0. And if I plug in the values of 0 and 1 into my second equation here, F2, I get 0 minus 2 squared, so that's 4. Plus, let me just write this out, so I get 0 minus 2 squared, so that's 4. 4. And then we have plus 1 minus 2 squared. So plus 1 minus 2 is negative 1 squared is plus 1. And then minus 4. And I'm taking the infinity norm of this. So that means it's the infinity norm of the vector 0, 1. And the infinity norm is the largest absolute value. So here the infinity norm of the tolerance in function would be 1. That's the value for my initial guess 0, 1. Okay, so let's calculate then. Let's do the first iteration. Iteration number 1. And all we need to do, right, we got our initial guess. Let me write the initial guess over here again. So x naught was 0, y naught was 1. And I need to evaluate now what delta x and delta y is. So let's write out the equation for delta x. So delta x is equal to F2. Well, here's my F2. So let me just copy this. X minus 2 squared plus y minus 2 squared minus 4. Okay. And then this entire thing gets multiplied by df1 dy, which was 2y. 2y. Minus f1. This is my f1. So x squared plus y squared minus 1 times df2 dy. So that was 2 times y minus 2. And then this entire thing is divided by the Jacobian, and the Jacobian was 8y minus 8x. Okay. And now what we have to do is substitute in these values, x naught equal to 0 and y naught equal to 1. So let me just mark here any time where there's the x value where I'm going to substitute 0 in. Right, that's all those locations. And the y naught equal to 1 gets substituted in anywhere there is a y value right over there. So let's do this. Let's substitute these values in. So I get 0 minus 2 squared plus 1 minus 2 squared minus 4 times 2 times 1 minus x squared, that's 0, squared, 1 squared. So 1 minus 1 times y minus 2, 1 minus 2 times the 2 that I skipped over. Divided by 8 times 1, 8 times 1 minus 0. Okay, that's just substituting these corresponding values into the equation. Okay, what do we get as a result? Here we have negative 2 squared, that's 4, plus 1 squared, that's 1, minus 4, 5 minus 4 is 1. 1 times 2 times 1 is 2. So that's equal to 2. And then over here we have 1 minus 1, that's 0, so that's all 0. And then here divided by 8. So 2 divided by 8, or 1/4. That's my delta x. Now the delta y is given over here. I just need to substitute in the functions and their partial derivatives. So it says delta y is equal to f1, which is x squared plus y squared minus 1, times df2 dx, that was 2 times x minus 2, minus f2, so minus x minus 2 squared plus y minus 2 squared minus 4, and the entire thing times df1 dx, so that's times 2x. And then we divide this again by the Jacobian, which was 8y minus 8x. Okay, substitute in the values as before. So I have here x is 0, so 0 squared plus 1 squared minus 1. You can already see that that's going to be 0 times 2 times 0 minus 2 minus, so we have negative 2 squared, 0 minus 2, right, plus 1 minus 2 squared minus 4 times, you make a little bit more room here, times 2 times x, well, times 0. Okay, divided by 8 times 1 minus 0. Okay, so let's look at this. 1 minus 1 here gives me a factor of 0, so all of that goes away. And back here I have a factor of 0, so all of that goes away, so it's 0 divided by 8. So the delta y is 0. Okay. All right, now I can update, found my delta x and delta y, I can update the solution estimate. All right, and the solution estimate, how to update it. x1, the new update, is equal to my old value plus delta x. So let's substitute the values in. It's 0 plus 1/4. So therefore x1 is equal to 1/4. And y1 is equal to the old y0 plus delta y. The y0 was 1. The delta y that I found was 0. So therefore, the new solution estimate for y is still equal to 1. And that would be the solution after one iteration. Now, am I done with this or not? Well, it depends on how accurate I want to be. I would then have to calculate, again, the tolerance in function, the infinity norm of this, for example. But that's pretty straightforward. I already did this for the initial guess. But let's calculate the other metric that we have, which is the estimated relative error. So the estimated relative error, right, is again a vector because I have two solution variables. So that will be x1, the new solution, minus the old solution, divided by the new solution. That's the first entry. And I can do the same thing for the y values. The new solution, y1, minus the old solution, y0, divided by the new solution, y1. So I want to take a norm of this, and let's use the infinity norm again. So I'm going to take the infinity norm of this. Okay, let's substitute the values in. x1 is 1/4, minus x0 was 0, divided by 1/4. That's the first entry, and y1 is 1 minus the old one was 1 divided by the new value is 1, and take the infinity norm of this. So what do I have as a vector? Quarter divided by a quarter is 1. 1 minus 1 is 0. That's my vector. I want to take the infinity norm of this, and you'll see that that would be equal to 1. So the estimated relative error infinity norm here on this is equal to 1. So probably too large for my liking, and then I would continue on using these values here, x1, y1, plug them into this equation for delta x and delta y, and then use those delta x and delta y values to update x1 and y1 to x2 and y2, and then keep on going that way until I have a satisfactory solution. Now, let's take this a step further. All right, we looked at two equations. Let's look at a full system of n nonlinear equations. So I have a first equation, f1, that is now a function of n x values, and that is supposed to be equal to 0. And I have a second nonlinear function all the way to an nth nonlinear function that I want to be equal to 0, and I want to find the solution that simultaneously solves all of these n nonlinear equations. Well, in principle, we attack this just the same way we did the two nonlinear equations. We use the truncated Taylor series as before. And if we do this, what we'll find is just a larger matrix on the left-hand side that still contains in the first row the first function. Now in each column it has the partial derivatives with respect to all of these x values from x1 through xn. So the first entry in the first column would be df1 dx1. The last one would be df1 dxn. And then the second row, well, takes the second nonlinear function and calculates all the partial derivatives. And we keep on going until we get to the nth row of the matrix that just takes the nth nonlinear function and calculates all the partial derivatives, starting with x1 all the way to the partial derivative with respect to xn. That then multiplies the vector of unknowns, which are the delta x's for each one of these solution variables, x1, x2, all the way through xn. And on the right-hand side, we simply have the negative of these functions evaluated at my current solution guess. Let's call the current solution guess xi, right, after the ith iteration. If we start out, then the I would be 0. That would be our initial guess vector. So this is a system of n linear equations that we, well, have to set up, and then we have to solve it, right? And we know how to solve this numerically. We'll just use Gauss-Jordan with partial pivoting that we developed in a prior module. So when we solve this system then numerically, we will get a delta x vector, and then in order to update the numerical solution, we just add this delta x vector to our current solution vector xi. That gives us then our new solution estimate vector xi plus 1. Okay, and then we repeat this with this new updated solution estimate xi plus 1 until the tolerance and function norm or the estimated relative error norm is below an acceptable value. Okay, so that's in a nutshell how you would solve a system of nonlinear equation using Newton's method. Now, Newton's method will likely converge if the functions themselves and all their partial derivatives are continuous and bounded near the solution, near the root. The Jacobian has to be non-zero near the root. Otherwise, the system doesn't have basically becomes singular and doesn't have a unique solution. So we can't solve that linear system. And as with any Newton's method or open method, in general, the initial solution estimate should be sufficiently close to the root. Now, what happens if that's not the case? Well, then you would have to try again with a different initial guess. What are the advantages overall? This method is typically very fast. But the disadvantage is that of any Newton's method, you need to be able to evaluate the partial derivatives analytically Although in a future module we will talk about how to do this numerically, but for now we will have to be able to calculate these partial derivatives analytically. And then the method might not converge. That could be because we didn't choose a good initial estimate, and the remedy for that is just to try again with a different initial estimate. Or it could be because one of these other failure modes, that the Jacobian is close to 0, and then the Newton's method will just not work. Right. Thank you for watching.